Right. So what we've seen before the break is that in the case where you had b equal to minus 0.3, that there was a period to sink. However, in the case b plus 0.3, this period to sink disappears and is replaced by something completely different, namely this beast here. So you no longer have a regular attractor, this is a chaotic attractor. And moreover, it's called the Hénon attractor because of the Hénon map. So what will happen is that if you have an initial condition, for example over here, then after a while, after a couple of iterations, you will get ever and ever closer to this attractor. And then you will basically follow this attractor. But by following this attractor, we do not mean that we like sequentially trace out the shape of this attractor like this. First of all, that's not possible because you would need a continuous map for this, and we jump in a discrete way. No, what will happen is that, for example, you will start somewhere over here on the attractor. The next iteration will bring you somewhere here, and then there, and then there, and then there, and then there. And if you keep on plotting thousands or millions of points of your orbit, eventually they will trace out this structure here, this attractor. And as you might guess from the complexity that's going on here, this is again a fractal structure. So you can zoom into this an infinite number of times, and you will never get to the end of all the complexity. So this is the attractor here. So again, this is not an orbit. We do not trace it out sequentially. Rather, we form it stroboscopically, if you want, by tracing out different parts of the attractor. Okay. By the way, there's no axis here, but this is of course the x-axis, and this is the y-axis. So this is your Hénon attractor. Good. This was a fractal structure. Of course, there's a well-known fractal structure that perhaps you've heard about before, which is this guy. As you can read, it's the Mandelbrot set, so I should have done it like this and asked the question, what is this? But I'm sure you've encountered this before in pretty science magazine pictures and stuff like that. So it's quite a popular figure. It's again a fractal. You can zoom in an infinite number of times and still get like this apple guy shape repeating itself, as you can already glimpse from this diagram here. And this is actually also a two-dimensional map. So let's see how this set arises, how this fractal arises. Well, the map that we're considering is actually a map where x and y are brought together in a complex number. So it's expressed as f of z is z squared plus c. So two-dimensional expressed in terms of complex numbers. How do we calculate the Mandelbrot set? Well, we first pick a value of c, and then we calculate the orbit of the origin. So we figure out what happens to the origin. So of course first you get c, then you get c squared plus c, and so on and so forth. So you keep on calculating this. Then there are two possibilities. Either this thing runs away towards infinity, or it doesn't run away towards infinity. And based on these two possibilities, you give the pixel corresponding to the point C, which you picked, a color. So for example, if it diverges towards infinity, you can color it white. If it does not, you can color it black. And if you like a bit more colors in your life, you can also, rather than having just two colors, black and white, you could, for example, replace white by different colors depending on the speed at which it runs away towards infinity. So this gives you some nice colorful figures, which I'm sure you've seen before. And then you can even cycle these colors and fly in the Mandelbrot set, and then really all sorts of nice psychedelic stuff. All arising from an extremely simple formula, so it doesn't get any simpler than this, right? F of z is z squared plus c. It's again a quadratic function, so a nonlinear function. By now, of course, you know that this is what you need, nonlinearity. But apart from that, it's a really simple structure. Okay, so this was the Mandelbrot set. I thought that any discussion about fractals would not be complete without mentioning this. Good. In the 1D system, we looked at sinks and at sources when we discussed the stability of fixed points. Of course, in 2D, there are also fixed points, but you have something a bit more complicated than sinks and sources. So let's see what you can have. Say, for example, that you consider a disk centered around a fixed point, and you want to figure out what's the image of that disk after applying the map once. So you could have the situation, for example, that you plot for all of the points in the disk the image after applying the map once, and then you get something that looks like this. Or you could have the situation where if you apply the map once, you get something that looks like this. So which of these two figures corresponds to either a sink or a source? So let's look at the first one, where the image of the disk becomes smaller. Who thinks that this is a sink, a stable fixed point? Who thinks this is a source? Who is afraid to think? Who is afraid to admit that they're afraid to? No, let's stop this. Okay, so this is indeed a sink, because the image gets smaller. All the points are getting pushed closer and closer towards the fixed point. So this is similar to what we had when we looked at what sinks were in a 1D map. And obviously this is an unstable fixed point. This is a source. However, the socket is not off with this, as they would say in Dutch, but not in English. What you can also have is a situation where you have the following, where the image evolves like this. So here it's a bit schizophrenical. There are some directions which tend to move closer to the fixed points, and other directions which get pushed away. So obviously this is something that can only occur in 2 dimensions, because 2 dimensions behave differently. So it's not something we encountered before. And therefore this type of point has a new name. It's called a saddle point. Why is it called a saddle point? Well, imagine that you're some sort of cowboy riding in the desert on your horse, and your horse has a saddle. And here I try to draw a saddle, failing utterly, of course, but okay, I guess you can imagine what I'm trying to draw here. You have the saddle. So say that you spill a drop of coffee from the cup of coffee that all the cowboys have, and it sort of falls on your saddle, and the horse is standing completely still. And initially it will move like this. It will move towards the center point of your saddle here, provided that you're not sitting there, obviously. But if the horse then moves a little bit, very quickly it will follow a trajectory like this. It will get pushed off to the sides of your saddle. So the shape of a saddle is indeed a shape which has attracting directions like this, and which has repelling directions like that. And if you project these trajectories here down below on the plane like this, you indeed see that you have trajectories which move like this. So here you can clearly see the attracting and the repelling directions. So this is a saddle point. So a saddle point, you cannot say that the saddle point is stable, right? Because it has one unstable direction. It's like a mix between an attracting direction and a repelling direction. So this is something new we also have in 2 dimensions now. Okay, to make the parallel with the 1D systems, in 1D systems we studied the stability of a fixed point by looking at the derivatives. Here in 2D we also want to do something similar. We want to basically look at the stability of these things by looking at derivatives, but derivatives basically means making your functions linear, so replacing a function with the tangent at the fixed points. So what we're going to do is we're going to proceed in 2 steps. First, we're going to look at stability of linear systems, boring linear systems, so there will not be chaos there. But then we will also study how we can move from nonlinear systems to linear systems, how we can linearize the systems, and then we'll bring these 2 pieces together to study the stability of fixed points of general, also nonlinear 2D systems. Okay, so this is the plan. Let's follow through on that plan. Let's have a look at the linear system first. So linear system, f of x, y. If it's a linear system, we're going to write this down also in a matrix notation. So let's call this the following matrix here. So let's say that these are the linear systems that we're going to study. what is a fixed point of this particular linear system? So a point, if you multiply it with a matrix, you get exactly the same point back, the same value back. What's the logical choice to try first? Since you don't know anything special about the matrix. How about the origin? Well, the origin 0, 0. If you plug in 0, 0 for x and y here, you still get 0, 0 back. So the origin, that's a fixed point. Perhaps some of you were thinking about eigenvectors here. Was anybody thinking of eigenvectors? There were people thinking of eigenvectors, and indeed they play a role here, because if you have an eigenvector, so if, for example, V naught is an eigenvector of this matrix A, then they also play a certain role, because V1, which is then A times V0, if V0 is an eigenvector, you can write this as lambda V0. And if you apply the map again, so if you multiply again with the matrix A, you have A times V1, but V1, we knew that this was lambda V0. And V0 is of course still an eigenvector of our matrix, so we get lambda squared V0. So if we restrict ourselves to eigenvectors, this 2D map basically reduces to a 1D map, where you could say that Vn is equal to lambda times Vn minus 1, where you just multiply with this eigenvalue lambda. So the eigenvectors play a certain role because they seem to simplify things a lot. Here you go from a 2D system to a 1D map. However, what happens for a general vector x, which is not by any chance or misfortune an eigenvector? So what happens then? Well, the eigenvalues and the eigenvectors still play a very important role, because if you dig deep in your memory to your very first courses about linear algebra, you know that if you have a system where the eigenvalues of a 2D matrix, suppose they are different and they're real, if you have real valued different eigenvalues, then it's possible to write your matrix A in such a way that it's the product of a matrix S inverse a diagonal matrix involving the eigenvalues, and then that matrix S again. So I hope this rings a bell from previously. You have encountered this in linear algebra courses, right? Now the good news is, here we're working with cases where we need to apply this matrix repeatedly, because we keep on iterating our map. So this means having A raised to a certain power if we want to calculate xn. So if we have A raised to the nth power, here you can clearly see that this will simplify a lot, because if you multiply them out, you have this S that will cancel with S minus 1, and then you have the product of these diagonal matrices, which is also quite simple to evaluate. So basically, A to the power of n is that same matrix here, and then a diagonal matrix where you raise the eigenvalues to the power of n, and then that same matrix here. So you can easily calculate xn, the nth element of your orbit, simply by having this beast here operating upon my initial condition, my initial vector x0. And here you clearly see what's going on, right? So we're looking at the origin. What will happen for initial conditions x0? If the origin is a stable fixed point, they should all end up near the origin. If the origin is an unstable fixed point, they should run away from the origin. And you can clearly see, because you have a formula to calculate a to the power of n directly, that the eigenvalues play a very important role here. Because if all of your eigenvalues are in magnitude smaller than 1, you can clearly see that if you raise them to the power of n, because they're smaller than 1 in magnitude, you will end up at the origin. So the origin will be a stable fixed point, a stable tractor. And this is what we had when we were talking about sinks. If, on the other hand, all your eigenvalues, they're bigger than 1, you will run away towards infinity. This thing will blow up. So this is an unstable fixed point. This is a source. But now, in the 2D case, you can have this schizophrenic situation where you have, for example, lambda 1 smaller than 1 and lambda 2 in magnitude bigger than 1. Then what you have is a saddle, because you have one attracting direction and one repelling direction. So you basically need to look at the eigenvalues of the matrix, and this will give you information about the stability of the origin as a fixed point. So this is a quite important property here. But I hear you say, or I hear you think, hey, wait a minute, this was only for situations where you had different real valued eigenvalues. What happens in other cases? Because what happens, for example, in situations where you have the eigenvalues which are the same, that can happen, right? You can have a matrix where the eigenvalues are the same. Well, then you can also prove, and we're not going to do that, you can refer yourself to linear algebra books, that in this case the matrix is not like proportional in the sense that you multiply with s and s minus 1, is not proportional to this diagonal matrix over here, but it's rather proportional to a matrix lambda, lambda 1. So it's a little bit more involved to calculate a to the power of n in this case, but you can do that for yourself as a fun little exercise, and then you can show that this basically becomes lambda to the power of n plus 1, lambda, lambda, n. You can easily prove that for yourself by induction, just taking the products of this matrix with itself. But here you also see this lambda raised to the power of, in this case, n minus 1 appearing. So the same conclusion holds, that if your eigenvalue lambda is smaller than 1, you raise it to an infinitely large power, you will end up at the origin. So this will mean that the fixed point, the origin, is indeed stable. So the same conclusion, lambda smaller than 1, you have a sink, and lambda bigger than 1, you have a source. Obviously no saddles in this case because you need different eigenvalues for this. So this is a pathological case. Right. What you can also do is look at the situation where the eigenvalues are complex conjugates, and so different. So then you can also make a factorization like this, because this basically relies on the fact that they're different, not so much that they're part of the real axis. But still, you can write it in a slightly different form, which gives you a little bit more insight into what's happening. You can basically show that your matrix then is, let's call it proportional to a matrix of the following form, A minus B, B, A, for complex conjugate eigenvalues, which you can then also write as follows: cosine theta minus sine theta, sine theta, cosine theta. And then this is indeed, again, the magnitude of the eigenvalue. You could prove that for yourself. So you see that in this case, multiplication by a matrix is basically a product of two different operations. One is multiplication by this factor here, which turns out to be the magnitude of the eigenvalue. And another thing is an operation which is described by this matrix. And this thing is called what's happening here, two vectors. The vectors are simply being rotated over an angle theta, right? So they don't change the magnitude, they just rotate. So if you keep on applying this matrix A over and over again, if you do it n times, you get a rotation over n times theta, and you get a multiplication by magnitude of lambda to the power of n. So again, the same thing holds. So in general, we can say that for all possible cases, as soon as your magnitude of your eigenvalues of the matrix is smaller than 1, stability, bigger than 1 is instability, mixed case is a saddle point. Okay. So this is quite important to know. There are a couple of exercises in the course notes where you have matrices, and I want you to ask if the fixed point is stable or unstable. I'm not going to do that in class. I hope you still remember how to calculate the eigenvalues of a matrix. If not, freshen that up, because there are some exercises on this. So be sure that you know how to calculate the eigenvalues of a 2x2 matrix, right? Okay. Good. Moving on, slowly barreling towards the end of this course, the end of the chapter. So let's take stock. We know how linear functions behave. We know that they have a fixed point at the origin. We know when it's stable and when it's unstable. What we still need to do now is figuring out how do we go from nonlinear functions to the nonlinear functions and linearize them in such a way that we can apply the algorithms that you've just seen before. So what's the equivalent of a derivative for the more dimensional case? Well, let's take stock again and let's build this slowly. If we have a 1D function, a 1D map going from x to y, we know, thanks to the derivative, that f of p plus h minus f of p, this will be equal to the derivative of f evaluated at p multiplied by h. And then you make a mistake on the order of h squared, right? So this is how we linearize 1D functions by moving towards the derivative. If we have 1D functions which are multivariate, for 1D multivariate functions, we basically go from a vector, x1, x2, and so on, to a single number y. Well, then you know we can linearize this as f of vector p plus vector h minus f of vector p. And then we need to bring the chain rule, or rather the rule of the derivatives of multivariate functions. Then we first have the f partial with respect to x1 evaluated at the fixed point p multiplied with h1. And then you repeat this for all of the independent variables, and so on and so forth, and you still make a mistake, which is on the order of magnitude h squared. Okay. But now, the most general case, the case that we want to study, is where you go from, for example, a 2D system to a 2D system, or rather from an ND system to an ND system. So not only do you have x1 to xn being mapped on a single function y, but rather you have a set of n such functions, y1 to yn. By the way, why am I not discussing the case here where you have different values for n and for m? So where you could, for example, have something going from a 2 vector to a 3 vector. Why am I not considering this in the context of what we're doing in this chapter? What would be the big problem if n and m were different? So why is your input space the same as your output space? Or to give you yet another hint, why is this then a map? Or does this need to be a map? Simply, if you go from a 2 vector to a 3 vector, what we're doing here is thinking about what happens if you keep on repeating the same procedure over and over again, if you iterate a map. But if you go from a 2 vector to a 3 vector, the next time you're not able to apply this map anymore. It's not a map, you're not able to apply this function anymore, because the input space is different than the output space. So therefore, we really need to have the situation where the dimensionality of the input and the output is the same. Otherwise, we don't have maps and we can't play around with applying functions recursively. So in this case, we have not a single value f, but rather a vector f. And this is essentially a shortcut that we can also write down in a matrix case. So basically, we write for f1 down what we have here, but in a matrix case, in a matrix notation, this becomes df1 dxn, df1 dxn, and we multiply with this vector, right? So this is just writing what I had for this case, but now we don't have a single function f1, we have a multitude of them, in fact n of them. So finally we build a matrix that looks like this. Okay. And again, we make a mistake on the order of blah blah blah, delta h squared. Now this particular matrix that we've introduced here, this basically takes a similar role as the derivative that we had in the 1D case. And it has a certain name. Perhaps somebody can remember that name from a previous life or a previous course. This matrix is called the Jacobian matrix. And in this particular chapter, we're going to write this down as follows. So d, with a vector sign above it, derivative of f evaluated in the point P. So this is the notation of the Jacobian that we'll use in this chapter. So in shorthand, we can write that f of P plus h minus f of P is equal to our Jacobian dfp times h plus some little mistake. Right, so this is in general. In our situation, we're studying fixed points, so where f of p is equal to p. So we can make that substitution. So if we have p and we apply the map once, we end up, of course, at p because it's a fixed point. If we look at the point in the neighborhood of p, namely p plus h, and we apply the map once, what this basically tells you is that f of p plus h is f of p, which is p, plus d f p h. So this is how points in the neighborhoods of our fixed point p gets operated upon by that map. If you bring all of this together, you can basically associate a linear map with this, a linear map which maps h, this deviation from our fixed point p, which maps h onto the vector d f p multiplied by h. And this is a linear map, right? So we have a matrix multiplication with a vector. So here we've seen how we can linearize our system. We basically construct this matrix involving all of these partial derivatives, and that matrix we use to form a map, a linear map operating upon this vector h here. And since we know what the stability of linear maps is involving this Jacobian, it should come as no surprise, although we don't do a formal proof here, that for a nonlinear system, if you want to study the stability of a fixed point, what you need to do, you first calculate the Jacobian, you look for its eigenvalues, and then see if they're in magnitude smaller than 1, bigger than 1, or a mixed case that give rise to a saddle point. By the way, another name for this mixed case, where one eigenvalue is larger than 1 and another is smaller than 1, these are called these are hyperbolic points. It's just a name. Okay. So again, there's some exercises in the course notes looking at nonlinear maps, asking you to calculate Jacobians and stuff like that. I don't think it's worthwhile that we spend some time here to do that together. These are quite simple exercises, but I would suggest that you do them at home, making sure that you know how to still calculate Jacobians, partial derivatives, and eigenvalues of 2 by 2 matrices. Good. With that hint out of the way, I would like to discuss the final part here of this chapter. Well, not really the final part of this chapter. So now the topic I want to discuss is stable and unstable manifolds. Sounds very science fiction-like, very Star Trek-like. So let's discuss that. What I'm not going to discuss is the section after that, which is called continuous maps. So Christmas is the season of giving. So the section about continuous maps, you can read that for yourself. But as my Christmas gift to you, I will not ask anything about that at the exam. So just skip the continuous map section. And let's wrap things up by talking about stable and unstable manifolds. Okay, Stable and unstable manifolds have everything to do with saddle points, because what I want to show you here is that saddle points, they may look like a curiosity, but actually the existence of saddle points and their properties, they tell you an awful lot about the dynamics of your system, so they're quite important to study. So let's have a look at the linear map with a saddle point, a rather artificially constructed map where you can immediately see the eigenvalues. So if this is a linear map, you can clearly see that if you have a point along the x-axis, that by applying matrix multiplication recursively, this will end up at the origin, right? So the origin is the attracting direction. So all of the points along the origin, the x-axis is the attracting direction, and the y-axis in this case is the repelling direction. And these attracting and these repelling directions, they are important, and this is what will give rise to stable and unstable manifolds. So for the linear case, the linear map here, the x-axis is called the stable manifold. This is the direction of stability, where everything gets attracted to the saddle points, and the y-axis is the unstable manifold. But let's make it a little bit more precise, the definition also for nonlinear maps. You can obviously generalize this to any dimension you want, but let's stick to 2D maps to make our life a bit simpler. So for a 2D map, if you have a saddle point, the map could be nonlinear. But what's then the definition of a stable manifold? Well, the definition of a stable manifold of a saddle point P is the collection of all of the points, of all of the vectors, for which the following is true, namely that if you apply the map n times to our vector v, that then the distance to the saddle point basically goes to 0 if n goes towards infinity. So in the limits of applying this map an infinite number of times, any point on a stable manifold should end up at the saddle point. So this is what we had in this case, the horizontal axis for this simple linear case. But this is a generalization of this, which is also valid for nonlinear systems. What are some properties of our manifold here? Well, first of all, the manifold, the stable manifold of a 2D map with a saddle point here is one-dimensional. So you also see this in the linear case. The stable manifold here was a line, so it's a one-dimensional object. That's not surprising. Again, these things here, I'm just giving them without proof. Proof is quite complex and quite elaborate, so let's not go there. So one property of the stable manifold in 2 dimensions is that it's a 1D structure. Another property of the stable manifold is that it's a manifold, which is of course a rather stupid thing to say, since we haven't really talked about what a manifold is. But let's now discuss what we mean by a manifold. Well, a manifold is a geometrical construct, basically something from topology, a structure which locally looks like a line. So if you zoom in, it should roughly look like a line. That's a very imprecise definition, but I hope that suffices for our purposes here. Let's give some examples of manifolds. And obviously, if you have the x-axis, that locally looks like a line, even globally, so that's obviously a manifold. Let's have a look at the letter O, for example. Would that be a manifold? Is this a structure which locally looks like a line? Who votes for yes? Okay, I'm not going to bother asking who votes for no, because indeed, if you zoom in here, this will locally look like a line. More letters. The letter I, written like this, is this a manifold? Who votes for yes? Who votes for no? 50-50 splits. Why do you vote for no?
But I'm not sure. Do you mean it has to be everywhere?
Yeah, it has to be everywhere.
I'm not sure for I at the top.
Yeah, exactly. So this does not locally look like a line everywhere, rather at the endpoints here it looks like half a line, and that's not allowed under the definition of manifolds. So then obviously letters like T, certainly not a manifold. You have the intersection here, and you have the endpoints. So a 1D manifold is basically a shape which you can draw without lifting your pen and without intersecting yourself. So here I get close, but luckily I get away. So this is like a 1D manifold. Good, so we know the stable manifold is 1D, it's a manifold, but rather importantly, it's also, it obviously should go through your saddle point here, right? And it turns out to be, through your saddle point here, parallel to the eigenvector of your, so parallel to the eigenvector of your Jacobian, for which the eigenvalue lambda was smaller than 1 in magnitude. Again, we can see that in the 1D case, in the linear case quite trivially. Here our eigenvector was located along the horizontal axis, and indeed our stable manifold is the x-axis is parallel, is actually equal to the horizontal axis. So this also holds in general for 2D systems, which are also nonlinear, but there it's possible that after a while it runs away from that direction. So only at the saddle point itself is it parallel to that eigenvector corresponding to the stable direction with an eigenvalue smaller than 1 in magnitude. That was the stable manifolds. What about the unstable manifolds? The unstable manifolds, well, we could try and conjure up a definition based on what we had here, like if the limit of applying the function an infinite number of times. Yeah, and then we run into a problem because it's possible that this limit does not exist of applying f an infinite number of times if you run away from the saddle point. You could end up in a period 2 orbit or run away towards infinity. So that limit does not really exist. So we need to find a different way of expressing the same concept without having the limit of applying f an infinite number of times. And there's a way around this by actually going backwards in time, if you want, by saying that our unstable manifold is the collection of points V, for which, if I apply not my map f, but the inverse of my map, if I go back in time n iterations, that then the distance to the saddle point P becomes 0 if n goes towards infinity. So here in this case, if you have an unstable manifold, something will happen. You will run away from your saddle points, either towards infinity or a chaotic attractor or whatever. But if you run that movie backwards in time, if you apply the map f-1, the inverse map, an infinite number of times, you should get back to the saddle point. That's because it's, in this case, an unstable saddle point. So this is a slight technicality here in order to come up with a definition for the unstable manifold, because the limit of fn in this case is not necessarily defined. What are the properties of the unstable manifold? Well, for a 2D map, it's a 1D thing. It's a manifold, unsurprisingly. And it's, in this case, also parallel to an eigenvector, but in this case the eigenvector corresponding to the unstable direction. Okay, so this is how they relate to each other. So for linear maps it was quite boring. We had the stable and the unstable horizontal and vertical axis that we had in the example. If you have nonlinear maps, stable and unstable manifolds can look a lot more elaborate and a lot more complex. Let's have a look at what they can look like. For example, for the case of the null map, you have stuff like this. You have a saddle point over here, right? And you see some sort of lines which would look familiar, like, hey, we've seen similar looking shapes before. And indeed, we have seen shapes before. Like, for example, this blue shape here. that should remind you very much to the things here, where I cheated to calculate them. And indeed they're related to this, because you can ask yourself the question, okay, in this case, I have white points which go towards my period 2 points, and I have black points which converge to infinity. You can ask yourself the question, what happens to points which are exactly on this boundary between these two? Do they go towards infinity, or do they go towards the period 2 points? Well, no, it turns out they go towards the saddle point. So again, without proof, but this shows you that so if they go towards the saddle point, that means they should be part of the stable manifold, right, by definition. So the stable manifold of our Hénault map with slightly different parameters, where do we have it? There we have it. So this is the stable manifold of our Hénault map, which is again a fractal structure. Okay. For the unstable manifold, which is here in red, you see indeed this looks a bit like our attractor, and indeed the attractor lies along the unstable manifolds of the saddle point. So we're not going to explain in detail why this exactly happens and where this comes from. The only message I want to bring across here is that saddle points, they're quite important in studying the dynamics of the system. You see here the attractors appearing and the boundaries between the different basins. And moreover, it turns out that if they intersect somewhere, of course they always intersect at a saddle, obviously, but if they intersect somewhere else, like for example in this case, it turns out that if you have one point where they intersect, non-trivial intersection, that then automatically you have an infinite number of points where they intersect. And these points are called homoclinic points, by the way. And then automatically, this infinite number of intersections between stable and unstable manifolds results in a system which is chaotic. So this is also an important conclusion which you can draw from all the stuff that's happening around saddle points. And that's actually due to a very famous French mathematician called Poincaré, who came up with all of this nice little theory. And there's an interesting story behind how he came up with that theory. And that story basically goes as follows. At the end of the 19th century, there was a Swedish king who, for his 60th birthday, decided to organize not a party as a Belgian king would do or something. No, rather this Swedish king, he organized for his birthday a mathematics competition. So basically he said to all the famous mathematicians of the world, send me a mathematics paper, and then I, or probably my jury, will select the most promising, the most interesting paper, and then the winner gets a prize or something. Okay, so all the famous mathematicians started to work on interesting papers, and also a guy called Henri Poincaré, and he was working on a topic involving the three-body problem. So you have the sun, the moon, and the earth, figuring out how they will end up due to gravitational interaction, stuff like that. So quite complex mathematics. And it turned out that actually Henri Poincaré won the prize. So the jury found his contribution the most novel and the most elegant. So you could think, okay, that's the end of the story, a happy ending. But unfortunately, the story did not really have a happy ending. Well, in the end it will, but not at this stage. Because what happened is that, okay, he submitted his work to this competition for the Swedish king, but he also wanted his colleagues, mathematicians, to read about his work. So he does what every scientist still does nowadays. He writes it up in a paper, and he sends it to some sort of journal to be published. So that's what he did. Poincaré sent in his copy to the most famous mathematics journal of the time. But then disaster struck, because at some point in time Poincaré got an email from the editor of the journal, who figured out, hey Poincaré, big problem, I've discovered a big error in your manuscript. And indeed the editor was right. Poincaré had made a big mistake in his prize-winning entry for the math competition of the Swedish king. So that's of course quite embarrassing. You won a prize with something which is wrong, actually. So any lesser mathematician would have jumped off a bridge, I guess, or no longer dare to come out in public. But not Henri Poincaré, because he started working feverishly on trying to correct his mistakes, figuring out what was going on, and basically rising from his mistake and from all the work he did to correct this, came this beautiful theory involving stable and unstable manifolds, homoclinic points, the attractors, all the stuff that you see here. So chaos theory basically was born from a mistake of Henri Poincaré, simplifying things a bit. So if I can give you one message for the course and the exam, or more important for the rest of your life, it's not to be afraid of your mistakes. So if you make a mistake, don't try to hide it or something, fess up to it, and realize that sometimes within the mistakes you make can be the seeds of something which is much greater, which was not predictable at the beginning here, just like in the case of Henri Poincaré. Okay, so with this message, I think I will wrap up this course, and the only thing that's left for me to do is to wish you happy holidays, happy seasons, greetings, Christmas, New Year's. Lots of success with the exams, of course, and lots of success with the rest of your life after that. Okay, thank you. Bye.